So let's talk about heat curves. So this is the heat curve for water. So we have temperature on the y-axis and time on the x-axis. We have the black is the heat curve and the purple is the cooling curve. So notice, since this is for water, we have 0 degrees Celsius marked, which is your freezing and melting point, melting, freezing, and our 100 degrees Celsius, which is the boiling point, where it boils or it would condense. Now let's talk about each part of this graph. So, when we're looking at line AB, we're going from a cold solid to a hot solid. So energy is added, the particles move faster, and the temperature increases. This is an endothermic process because energy has to be pumped in. So you can imagine your solids vibrating very slowly when it's cold, and as the solid warms up, it's still a solid and it's still vibrating, but it would be vibrating much faster. So for simplicity reasons, I'm using just a single dot to represent our water molecules, but please remember water would actually have 3 circles because the formula for water is H2O. Now, so we talked about AB. When we go on to BC, this is where a phase change happens. We have melting happening. So we're essentially going from a hot, quotes, solid to a cold liquid. So 0 degrees Celsius solid to 0 degrees Celsius liquid for water. Energy is still being added. The intermolecular bonds are broken as the particles gain energy. Now remember, intermolecular are the ones between the water, so water to water bonds. This allows for the phase change for our vibrating solid particles to be able to go all kinds of crazy and spread out and kind of go around each other in that liquid phase. Remember, 2 whooshies are our symbol for a liquid. Now, when we move on to the CD line, so we're now here, we are in the liquid phase all the way. So all we're doing is going from a cold liquid to a hot liquid. Energy is added, particles move faster, and the temperature increases. It's still endothermic, and we can represent that they're moving faster by putting longer whooshies so it looks like they're zooming. Now, when we move to our DE, we're on another flat area. This is another phase change, so this time we are evaporating. When we go from a hot liquid to a cold gas, energy is still needed to be added, but we're now breaking all the rest of the intermolecular bonds, and this is an endothermic process, so we're going through the phase change of evaporation. So our hot liquid molecules will burst into that gaseous phase, but in relative sense, they are still a cold gas. Don't forget, 2 is liquid, 3 is gas. Very important when you do those particle diagrams. So when we get above the DE line to the EF line, we're still in the gaseous phase. We're going from cold gas to a hot gas. Remember, cold and hot are relative. Energy is still being pumped in. Particles are still going to move faster when you heat them up, and so the temperature is increasing. Still endothermic, and you can represent this process by changing the length of your whooshies. So if we now start back over here at the top, and we work our way down the cooling curve, it's essentially the same things, but there'll be a key change in the wording. So if we're going from K to L, we're going from, ooh, sorry, wrong order. Swap those. Aha! If we go from G to H, we're going from a hot gas to a cold gas. So energy is released. Particles will move slower. As they get closer, they move slower. They're going to start getting close together, and their whooshies are getting shorter. It is exothermic because when it loses that energy, it's got to go somewhere. It goes out into the surroundings. So once we start getting cold enough, energy still is being released. But once the particles get close enough together, they get closer and closer, they get more dense, and they undergo condensation. And then they go from being a cold gas to a hot liquid. Though, if you look on your graph, your temperature is still at 100 degrees. That's why we're using these relative terms. So H would be relatively colder than a gas way up at G. Still exothermic. So we move on, and we're now going from I to J. So we're just cooling from a hot liquid to a cold liquid. Energy still being released. Particles move slower and the temperature decreases. Still exothermic because that energy has to go out to the surroundings. We can best represent this with shorter whooshies. Continuing, now we're hitting another flat line. So on the heating curve, this was our melting, but now we're going from the liquid to the solid phase, and this is our freezing. Energy still released. Now we're going to form even more intermolecular bonds because the particles are going to be even closer together, and they're just going to take that solid form, but they'll still be vibrating quite quickly comparatively to a colder solid. Our last leg of our graph is our KL leg, where energy is released. The particles are still moving even slower as the temperature decreases. Still exothermic, but our vibrations are getting smaller and smaller and smaller.